Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. In today's lecture, we will discuss the electronic structure and the optical properties, and the relationship between the electronic structure and optical property. This lecture is also linked with the previous lecture, where we were studying the property of nanomaterials and their applications. Today's lecture is basically devoted to the electronic structure and the optical property of nanomaterials. This lecture has been taken from the course outline of nanophysics and technology, which has the course code of PHY445. Normally, this is a band structure of the semiconductor, and the band gap is actually the distance between the valence band maximum and conduction band minimum. It varies from material to material. Here a TiO2, pure TiO2 is considered, and the anatase phase of pure TiO2 is considered because in TiO2 the rutile has a band gap of 3.0 electron volt, while anatase has the band gap of 3.2 electron volt. So if you want to shift an electron from the valence band to the conduction band, so we can do it with the help of electromagnetic radiation. So the electromagnetic spectrum is very wide, and only that particular radiation would be utilized whose energy is equal to the band gap energy. Here in this case the band gap energy is 3.2 electron volt. So if we consider that which wavelength will be suitable for shifting the electron from the valence band to the conduction band, that will lead to the absorption of that particular photon. So we can see that the wavelength comes in the region of 387.5 nanometer, and this comes in the range of ultraviolet light. So this means that only ultraviolet light could be utilized to shift or migrate an electron from the valence band toward the conduction band. So this is actually absorption process. In the when the electron come back from the conduction band to valence band, so the same amount of energy is emitted in the form of light, depending on that particular wavelength, which is corresponds to the difference between the valence band and conduction band. So this is the simple electronic structure of a semiconductor material, where light of suitable wavelengths falls in the semiconductor material and shift an electron from the valence band toward the conduction band, creating electron hole pairs. So if we consider here we have a 3.2 electron volts there, so I means the ultraviolet light could be utilized for this purpose. We can also see that we can also change the band gap of semiconductor material, and this is possible with the help of doping or some other process. I means doping or creation of vacancy. So there are different processes for that, but one of the process is the doping, through which we can this band structure of the semiconductor could be changed with the help of doping or creation of vacancies. So that is possible. So it means that we can tailor the band gap of semiconductors, and with the help of that we can also change the energy required or the wavelength required for the creation of electron hole pair. So it means we can easily shift the absorption area of material from ultraviolet to visible or to some other energy range. So that is possible with the help of doping or adding some dopant material, or with the help of some creation of vacancy of that bulk material. So here in this case we can see that with the help of doping Y and deuterium and nitrogen in the bulk of TiO2, some isolated states are created above the valence band. Here we can see the N2p states is created due to the N dopant in the TiO2. So this isolated states help in migrating the electron from valence band toward the conduction band. So in that case we will have a type of stepwise transition of electron, because initially electron will be migrated from the valence band toward the isolated N2p states, and then in the next step the electron will move from the N2p states toward the conduction band. So similarly, in some cases the band gap is reduced, means the distance between the valence band maximum and the conduction band minimum is reduced. So that is also possible. So that is just like we can see in the case of deuterium doping, due to the addition of Y40 states in the band in the valence band. I mean the Y40 states mix with the TiO2 state, so that leads to the shifting of the valence bands toward conduction band, and finally the outcome is that the band gap is reduced. So this reduction in the band gap allow visible light photon for absorption, leading to the shifting of the absorption edge toward visible regime. So it's also possible that we can change the electronic structure of the material, and that will lead to the changing the optical properties of the material. So it's both linked with each other. So here we can see the experimental results where the doping, or maybe doping shifted the absorption edge toward visible regime, or maybe, and that is only possible with the help of the changing the electronic structure. So in previous slide we observed that the electronic structure has been changed with the help of doping, and here from the experimental results we found that the absorption edge has been shifted towards another wavelength, that is comes in the visible regime. So this means the electronic structure is strongly linked with the optical property, and changing the band gap or altering the band gap will leads to the change of the absorption edge, and that is why we can allow the semiconductor to absorb a wide range of wavelengths. So how the size of the nanomaterial affect the optical property, that will be the discussion on this slide. So it means that how what causes the reduction in size that change the optical properties of the material. As we know that the bulk metal sample absorb electromagnetic radiation, maybe in case of in the visible regime. So thin films of metal may partially transmit, and just because there is insufficient materials to absorb the radiation. If we see the gold films of having around few second of nanometer, tenths of nanometers thick, become partially transparent. So apart from insufficient material effect, there are important phenomena which comes into play in nanomaterials. So these include dominance of surface plasmas, as we discussed even in previous lecture, that the surface atom increases compared to the bulk atom. We are going through reduction in the particle size. So magnitude wise, as we have mentioned, how there is great change in the surface atom compared to the bulk atoms when we are coming toward the when we are coming to the reduction in the particle size. So the two of the factors that are responsible for that are the surface plasma and quantum confinement, that play the major role. Just like in semiconductor, quantum dot optical absorption emission shifts to the blue or the higher energy as the size of the dot decreases. So this size reductions is more prominent in the case of semiconductor as compared to metal, because basically we can get interesting light or phenomena from the semiconductor because of the quantum size confinement. It is because the quantum size confinement effect become more important in metals is at smaller size than semiconductor crystals. So semiconductor nanoparticle and films, how it affect the optical response of the materials. We see how the size decrease and how the optical response of that decrease. It's greatly linked with the energy gap, or actually the difference between the valence band and conduction band in semiconductor, and in isolated atom actually it is the difference between the lower energy level and higher energy levels. So that is the most important thing. So which gradually come from single atom towards semiconductor or a bulk material. So we can observe how the decreasing particle size or the increasing particle size, I mean increasing the atoms, will lead to populate the bands, I mean populate the states, and decreasing the size will try to isolate the bands. So here we can see that decreasing size, the electron get confined to a particle, that is particle confinement effect, and it leads to increase in band gap energy and band level get quantized discrete. If we see in case of semiconductors, the electron can move in that particular band that is allocated for it, means the in conduction band, because it has a particular width. But in case of a single isolated atom, there are fixed discrete level for it, in which the electron can move, except it cannot move. So it means that electron is coming from the continuous region, that is in case of semiconductor, and continues with the particular limits towards a discrete level. So the surface states of the steps which lie in the band gap becomes important, and that alter the optical property of nanocrystals. Here we can see, in this case this is a semiconductor materials. So this is the valence band of the semiconductor, and this is the conduction band, and the difference between the valence band and conduction band is the band gap. Is we are reducing the size of the nanoparticle of that material, you see the states become isolated because the number of atoms in that particular nanoparticle reduce greatly. So that is the nanoparticle, the band gap becomes isolated, and that is why we get interesting colors. And when it is clustered, though, there is further reduction in the population of that states, and that leads to the discreteness of that state as well. When we come finally to a single atom, so here we can see a discrete energy level at the lower energy level, and even in the and at the upper energy level. So only particular or fixed wavelength is emitted in that particular case, because the discrete level even in the lower energy level and even at the higher energy level is fixed. So that leads to the quantum size confinement effect. So we can consider some of the semiconductor material, just like GaAs, gallium arsenide, where it is in nanoparticle size, and its size is around 7 to 15 nanometer. So there is a broad excitonic peak at around 526.0 nanometer, and that leads to the band gap of 2.36 electron volt, and it is possible because the energy gap of the nano GaAs has been blue shifted by 0.93 electron volt, but actually in the bulk band gap is 1.43 electron volt due to the quantum size effect. So here we can see how there is great effect in that. If we see here is a curve between the wavelength and the absorbance of that material. So we can see here is a bulk gallium GaAs. So this is the spectrum or the curve of the bulk GaAs. But if we reduce the size, so there is another peak is found at around 426.0 nanometer, and that is possible due to the reduction in the particle size. And as we see as we saw in the previous slide, in this slide, here we can see that the reduction in the particle size change the bands into states. So that is why we can get interesting optical property from the nanoparticle of different semiconductor material, and that is possible with the help of excitonic absorption. So enhancement of absorption or the range of wavelengths seen here is the enhanced oscillator strength, that is dimensional quantity to express the strength of the transition. So this excitonic peak is broad due to the size distribution of the crystallites. So what happens when we reduce the size of the particle? The density of state become more quantized. Here we can see in the previous case where we show the density of states of the semiconductor materials to study the electronic structure of the material. When we adopt a single atom, so there is a single N2p state that is created due to here. Let me show you, and coming back to the slide. So we can see that a single N2p states here. In this case, this is the single N2p state, that is isolated states has been created just above the valence band, because here in this case we have doped a single N2p atoms, and the isolated states has been appeared in the band gap of TiO2. So what happened actually when there is the reduction in the size of the particle, the density of state become more quantized, and that leads to the band gap shifts to higher energy, and that means shorter wavelength. So absorption spectrum shows a blue shift. Here we can see how the absorption spectrum changes. So if we reduce the particle size, this is actually the absorbance of different vertical size shows the absorption, and horizontal size shows the wavelength. And here we have material with different particle size. When the particle size is very high, that is 9 nanometer, would happen, and we see this shift, how the shifts are created. So coming toward the decreasing particle size, for the particle size of 5.5 nanometer would happen, the peak is created, but that is its intensity is low. Coming more toward the lower particle size, the peak is at found, and then found at the end we can see that at 3 nanometer there is huge peak that is created due to that, and we can see clear peaks in the case of lower particle size. So this is some of the data that has been taken from the spectra of absorption spectra of PBSE nanocrystals. So one of the other optical property that is widely used and it is of interest, that is a photoluminescence. So photoluminescence, in case of photoluminescence, material is excited with the help of electromagnetic radiation, and that is followed by relaxation to ground state by emission of photon, and we can observe or we can enjoy different colors out of that. When the semiconductor relaxes to the ground state by the recombination of electron and hole, what happens? This leads to the creation or the emission of photon. As we discussed before, that is not possible for an atom or for a system to remain in excited state for longer time. So what happens when an electron is excited from valence band toward the conduction band? So it cannot remain for longer time in the conduction band, so it will come back to the valence band to combine with the hole, and when it comes back to the valence band, so the energy, a photon is emitted whose energy is equal to the difference between the two energy levels. So if the photon energy lies in the range of 1.8 to 3.1 electron volt, the radiation will be in this visible range. So there is a good relationship between the band gap and the wavelength of the emitted photon. So if we see that the band gap is in the range of 1.8 to 3.1 electron volt, so the radiation or the photon that will emit it will be clearly visible, and that will be in the visible range. This is called as luminescence. So by changing the size of the nanoparticle, the frequency of emission can be tailored. It's very easy to change it. So as the size of the nanoparticle decreases, there is a blue shift in frequency. So we have a property of core shell nanostructure. How we can have optical property from the core shell nanostructure, and how when a semiconductor is placed on other semiconductor material. So that is possible, and the luminosity properties are a characteristic of that particular core material. So the shell leads to an enhancement of the luminescent property of the core, that is actually the luminescence of the nanoparticle, and the luminescence of the nanoparticle are well defined with narrow spectral ranges which depends on the particle size. So deposition of a semiconductor with a larger band gap than that of the core typically results in luminescence enhancement due to this suppression of radiation-less recombination mediated by surface states, and in some cases we will have radiation-less recombination, and it depends upon the difference between the energy level, and in some cases we will have dissipative recombination. In the case of dissipative recombination, the energy will be dissipated in the form of heat. We cannot lose the energy. We must have the law of conservation of energy must be satisfied. So the energy, when there is a recombination between the electron and holes, the energy will be wasted in the form of heat. So that is called as a dissipative recombination. Just like in case of CDS coated with SO4, then is coated with series. So this is the semiconductor coated and a semiconductor material. So the band gap could be tuned in the near infrared region, which can be useful as an infrared biological luminescence markers. So we have fluorescent material from core shell quantum dot, and it has very interesting property, because when we reduce the particle size, what happen, the colors or the lights that is emitted has different wavelength, and we can enjoy different colors. So here we have an example of CDSE nanoparticles, and this decreasing the particle size allows it to emit different interesting colors. Just like for the case of 5.5 particle size of 5.5 nanometer, the color is red. I mean, it's just different wavelength, and it is blue shifted when we are decreasing the particle size. And finally, at the particle size of 2.3 nanometer, we can get around blue colors. So this is for the when the Z and S is quoted above the CDSE. So here we can observe the the curves between the intensity and the wavelength of that, and we can see the peaks that are really visible to us, and that is created due to the reduction in the particle size. And this is the actually the enhancement due to the shell. And in some cases we have dashed lines that CDS nanoparticle shows that how we can reduce the particle size, and that will create the absorption peak in different wavelengths. So we can get interesting colors by reducing the particle size. So this is something about the relationship between the optical and the electronic structures. So I hope we can start some fabrication of nanomaterial in the next lecture. Thank you very much.